This afternoon we have a specialist session, a student session, with 3 young speakers. And the first is Oleksandr Iaroshenko from Penn State University. He talked about reduction from full GINZBURG-LANDAU to harmonic map functional in a circular domain. We have 2 minutes.
Thank you. You already know my name and the title of my talk. So I'm going to talk about the problem that was announced on Tuesday by my advisor, Professor Bernard, in relation to the work that he was explaining. So this work in collaboration with Professor Dmitry Golovatiy from Moscow University and Dr. Volodymyr Rybalko from Institute of Lower Temperature in Kharkiv. I'll start. I'll quickly remind you the motivation of this problem. So that's what was Tuesday's talk of Professor Bernard about. Then I'll formulate you the problems that we are focusing on in this presentation. And then we'll go quickly through the proof of it. This proof will consist of 2 parts. First part is actually considering harmonic map minimization problem. It's very nice. It does not have a nonlinear term. And there is an explicit solution here, so I'll give you some precise result of it. And the next part is what we call energy decomposition. We'll decompose energy of full minimizer in terms of harmonic map energy plus some remainder. And the further work is just analysis of this remainder. So we'll get some upper and lower energy bounds on it. And as a result, we'll prove that there are no bulk vortices in our domain, and the main goal of our work will show that the degrees of whole vortices are the same. So let's start. The general problem is a minimization of full GINZBURG-LANDAU functional with magnetic field in the domain with periodic lattice of small holes. In the certain relation between parameters such as distance between holes, radius of holes, the magnitude of the external magnetic field, Leonid Berendt and Volodymyr Rybalko were able to prove that if we consider a gamma convergence in this minimization problem when period of lattice goes to 0, as a result, we can observe that the limit in vorticity, d of x, that's just a Wick limit of vortex density, has this structure of nested subdomains. So that's what you heard on Tuesday. So to mention here, we consider external magnetic field weak enough so there are no bulk vortices, but it's strong enough so some vortices can appear inside holes. So that's actually we call here vorticity. So whole vortices is just a winding number around the hole. So there is no zeros of the function, but there is a winding number around the hole. So this result was proved under the important conjecture. So actually, instead of full functional, the harmonic map functional was considered when we assume that modulus u equals 1. That's what we call harmonic map functional. So it's harmonic map when we are talking about functional without magnetic field, but we're still calling it harmonic map 1. The conjecture is the following, that the degrees of whole vortices of minimizers of both problem, harmonic map minimization problem with restriction modulus equals 1, and general problem are the same. What can we say about this conjecture? Some result about degrees of whole vortices was shown in the paper of Sten Alama and Leah Bronsart. They showed that if there are a finite number of holes with fixed size, and the magnetic field is bounded, just some constant, then there is just a strong convergence of minimizers of general problem to minimizers of harmonic map problem. When actually there is no period of lattice, there is convergence when epsilon goes to 0, the inverse of GINZBURG-LANDAU parameter. And in this case, strong convergence of minimizer just implies the equality of degrees. So in our case, the situation becomes worse because the field will blow up in this limit. And to prove this conjecture, we start with a model problem in the circular domain with one hole. So that's what this presentation will be about. So let me give you the precise formulation of the problem. We consider this domain with whole of external with domain that is disk of radius 1 with whole of radius delta. That is our control parameter here. The external magnetic field is of order logarithm delta, so it blows up when delta goes to 0. And we consider the relation between inverse of GINZBURG-LANDAU parameter and radius delta in a certain way, so the logarithm of epsilon is much greater than logarithm of delta in absolute value. So why do we need, what this condition actually means? So as you know from all the previous presentations, that size of the core of the possible bulk vortex that can appear inside domain is epsilon. This condition actually says that epsilon is not even smaller than the size of the whole delta, but it even smaller than any power of delta that we'll use in our proof. So this whole is bigger than core of a vortex. And another thing that in simply connected domain, we know that first critical magnetic field is of order logarithm epsilon. That's the field when first bulk vortices appear. So if we consider field of order logarithm delta, it's lower than first critical magnetic field, and no vortices. We expect no vortices to appear outside the hole. But that needs to be rigorously proven because we consider not simply connected domain. And we consider the harmonic map functional. That is functional where potential term disappears because we put the restriction that modulus u equals 1. We consider two minimization problems, minimization of general functional and minimization of harmonic map problem with S1 valued function u. And our goal is to prove that the degrees of the whole vortices of both minimizers coincide. So, as I said, this proof consists of two parts. In the first, we consider harmonic map problem. There is no nonlinear term, and actually it can be solved explicitly. We can explicitly find this minimizer. Also, in many presentations during this week by Tiziana De Giorgi, by Leah Bronsart, by John Chapman, you saw this kind of approximate vortex where just e to the I defy the order parameter, and there is certain radially symmetric magnetic field. So we are looking for this radially symmetric solution of harmonic map problem when we prescribe the degree d. So the minimizer we denoted as UDAD, the minimizer of such problem. And now we can consider energy on this minimizer as just as a function of this d. So just function of integer. And the following theorem says that, so we can solve it explicitly, as I said. And this energy as a function of d has the following form. So you can see that that's a quadratic polynomial in terms of d, where coefficients in front of d squared and d are of order logarithm delta, and the free coefficient is of order logarithm delta squared. That comes from h external squared. What it means, if we change the degree, so that's a leading term in the energy. It's high. The terms that consist degree, they are of lower order. So if we change degree, we are changing energy on the lower order. So we need somehow to compare energies of harmonic map minimizer and full minimizer with different degrees to show that these degrees are the same. So we cannot just directly compare them because the leading term does not know anything about degree. So our goal will be to somehow get rid of it and compare energies on the lower level. So moreover, the theorem says that under this relation, we can state that there is a unique minimizing degree, d star, such that energy, like from here, they're different by logarithm, by something of order logarithm delta. Why do we need this condition? D star actually can be found as a nearest integer to C star sigma. So obviously, if distance from C star sigma is exactly in between of two integers, so that's what fails this condition. You can see from this picture, in this case, we cannot uniquely determine what will be the minimizing degree. Both of them have approximately the same energies. But if the distance from this vertex to the z plus 1/2 is strictly positive, we can always find unique minimizer. Here is m plus 1, as you can see. So here we need this additional condition. Next step is energy decomposition. Energy decomposition, what is the goal of it? So as I said, we need somehow to compare energies on lower level. So what do we want? We want to decompose energy of full minimizer UA in terms of this harmonic minimizer U star A star that I found here, and consider the remainder. So we want, we want the following. If we subtract these energies, we want to cancel term of high order logarithm delta squared, and to have difference of them of order logarithm delta. Then actually the degree will play the crucial role. Changing the degree, we are changing this much. So this will allow us to show that degrees are the same. Main tool in this proof will be ball construction method. So this method was described by Gerard, by Sandier in different variations. So I'm using the method that was described in the book of Sandier and Serfati. What is the main thing about this method? It localizes the subset of our domain where modulus U can be small. That's what you also saw today in one of the presentations. It localizes this subset of omega in small disks such that their total radii are very small, and it gives some lower bound on energy inside these disks. So that's a precise formulation of this of this ball construction method, this proposition. So you can see that energy on each ball is bounded from below by logarithm epsilon, that's a GINZBURG-LANDAU parameter, times the degree of possible bulk vortex. So we have some disk, Bj, and dj is just a degree in this disk. So how we'll use it? First we do the decomposition, as I mentioned. So this idea of this decomposition follows, again, ideas in Sandier and Serfati book, and also in the paper of Sten Alama and Leah Bronzer that I mentioned. So we decompose full energy in terms of harmonic map energy and some remainder here. So functions v and b are just factors when we factorize u in terms of u star and a in terms of a star. What do we do with this decomposition? So this is full energy, this is constraint energy, so one is obviously less than another one, so we just subtract them, and this equality turns into inequality with function with energy f. They're just functional with the same GINZBURG-LANDAU functional with zero external field. Working out this integral, analyzing it, we can write this formula that actually gives us kind of upper bound on f in terms of possible degrees of bulk vortices dj's. So far we haven't get rid of them. And dv, that is degree of function v. Degree is additive, so degree of function v is just difference between two degrees d and d star. Our goal is to prove that they're the same, so it's equivalent to show that dv is 0. So how are we going to do that? We fix a number alpha greater than 1, and actually at the end we'll use that we can the fact that we can choose this parameter arbitrarily large. So we fix this parameter and consider two cases. So if dv, degree of the whole vortex of function v, is bounded from above by sum of all possible bulk vortices. This case is easy, so we can quickly prove that there are no bulk dj's cannot be 0, and if dj's are 0 by this bound, it implies that dv is 0. So here I will not give you details, it's just like pretty simple implication here. Another case is more difficult. If dv is unbounded, we don't know anything about it. To understand how it can behave, we show the lower bound now on this energy f. So the previous page showed you the upper bound on f. Now we show the lower bound on energy f. That consists of part coming from ball construction method, so energy inside balls, and this term that comes from energy outside balls, outside these bad disks that ball construction method gives us. So here you can see that lower bound consists of term dv squared, and upper bound consists of term dv. So at the end we'll have some kind of quadratic inequality for dV that will help us to show that dV is 0. So what do we do with this? We just combine these two estimates. So that's estimates that we just have the lower bound and the upper bound. What can we say about them? All magnetic fields, H external and H star, that is magnetic field we can be explicitly found the first part of the problem. They all afford a logarithm delta. So if we're talking only about the orders of all terms here, so that's how this inequality can look like. So it's dV squared times logarithm delta, and dV times also something for the logarithm delta. In the right-hand side, we have a leading term, dj, or it should be dj, times term of order logarithm epsilon. So this is parabola with, actually, this term is positive. You can see it from here. This parabola with branches facing up. So it can be negative. So this term is obviously negative if or at least one of the j's is non-zero. This term can be negative. Left-hand side can be negative only if you're in between of two roots of parabola. So coefficients are of the same order. That means that top of vertex of parabola and both roots are bounded, just finite. That means that this thing, when it is negative, it can be only for the logarithm delta. But this term decreases to negative infinity with order logarithm epsilon that is much, much higher. You remember our initial condition. So that's why we can state that we cannot bound this term by something of order logarithm delta. And that's why all dj's should be zeros. So that proves that there are no, like, all possible balls that we constructed, they all have 0 degree. So there are no bulk vortices. Now we rewrite this left-hand side. Again, we compute this explicitly and can rewrite this left-hand side just as this inequality. So dV squared less or equal some constant times dV. So I remember size difference is distance to z plus 1/2 is some fixed number, strictly positive. So this term is strictly less than 1. And theta can be chosen arbitrarily close to 0. Alpha can be chosen arbitrarily large. So this term can be chosen arbitrarily, so it's greater than 1, but it can be chosen arbitrarily closer to 1. So we choose it in that way so that the product is still some number that is strictly less than 1. Then we have an equality dV squared less or equal this b dV, it's less or equal than 1, plus something small. That is, of course, strictly less than dV if dV is non-zero. So if dV is non-zero, we have inequality dV squared strictly less than dV, and that's difference between two integers, that degree. If it's integer, it can be only 0. So that finishes the proof, dV equals 0, and that means that difference d minus d star is 0, so d equals d star. So we actually proved that both degrees are the same. So to conclude, under certain relation between parameters of the problem, such as GINZBURG-LANDAU parameter, field, magnetic field, and size of the hole, we were able to show that the degrees of hole vortices are the same, but we needed this one more additional condition, that distance to z plus 1/2 should be strictly positive, because in this way we cannot uniquely determine the minimizing degree. Moreover, we showed that there are no bulk vortices in the domain, so the equivalence of these degrees actually means effectively tells us that all possible vortices have the same degrees. How can we develop this result? That's what Professor Bernd also was talking about. So first, here we considered model domain. So we need somehow to extend this result to the arbitrary domain with periodic lattice of holes. Also, we can consider some different relation between parameters, like to play with size of the hole and magnetic field, taking them of different order. And also, you saw some numeric results about what can happen if you consider the random location of holes. Okay, so that's all I wanted to talk to you today. Thank you for your attention.